The integral test for convergence is a whole lot of fun, but you have to know these three things that I keep repeating over and over and over again. Okay, that was a really lame song. The integral test for convergence is used to decide if a series converges. You are really embarking now on a series, pun intended, of lessons in which we will be determining if a series converges. And just to review what that means one more time, a series is going to converge if I have some series, and we're going to start it, it's going to be written very sloppy, from 1 to infinity. Infinite series is what I'm referring to, of some explicit formula, a sub n, and it equals a number. That would converge. But if it equaled infinity or negative infinity or back and forth, some of them alternate, that would not converge, that would diverge. So what we're going to do is determine if a series converges or not. Now I also want to point out that there are some series that we have dealt with very recently, geometric series, for example, where I don't want to spend too much time on this, but I could do this and I could say, oh, 1/2 to the n power. I can do that and I could say, oh, this converges, but I can find what it converges to. Like I could add up 1/2 to the 1 plus 1/2 to the 2 plus 1/2 to the 3 plus 1/2 to the 4. And you do that enough and you're going to end up, in this case, actually with 1. It's kind of neat. Picked an easy example. And I can find what it converges to, but this one was geometric. And because it was geometric, I have a formula for it. But not everything does. So just because I know something converges doesn't mean I know what it converges to. And that's the easy pitfall with this one. Okay, let's jump in. 3 things, super important. In order for me to apply this test, there are conditions that have to be met. And condition number 1, the function, let me rephrase, the series has to be positive. Now I said function because of what's about to happen. We're going to rewrite a series as if it was a function. For example, if I was doing this one the same way I'm going to do some of the other ones, then I would say, okay, well, this is my series, a sub n, my explicit formula that gets me to any term would be this, but in function form, it would be 1/2 to the x. It's really not a big jump to make that, okay? But in order for me to do this, the series has to be consistently positive, or the function actually. It has to be continuous as a function, because discontinuities mess things up, and it has to be decreasing, and decreasing really because it has to pass the previous lesson, the nth term test. I need to have the, here we go, scrap paper again. The limit as n approaches infinity of whatever this is, had better be 0. It better be getting down towards 0, and because it's positive, it's going to be getting towards 0. If it was just simply decreasing and wasn't restricted to the positives, it could just be going down into the negatives and going towards like national debt territory. Anyway, all right, let me sum up everything that's just happened. Sum up, get it? Because it's a series. I'm going to rewrite a function, a series, like a function, and then I'm going to treat the series like the function and find the integral from 1 to infinity. Okay? However, the function itself has to be positive, continuous, and decreasing for all the x's greater than or equal to 1. And here, the explicit formula is equal to, or the equivalent of some function. Then this, the equivalence, this is series to function, they're going to do the same thing. Either they both converge or they both diverge. This one's not one of my favorites, I'm just being honest with you, because there's so much work that goes into it. Not one of the faster ones, but it works. It works very well. So here's what we're going to do. Let's start this next one with the purple pen. And we are going to rewrite this as a function. Okay, well, I'll look at this and I'll say, okay, have I met 3 conditions? Is this positive? Yes. So I'm going to actually start my final answer down here. And I'm going to just make it all super wordy. Like it's going to explain everything. Do they all have to be this way? No. All this says is, does it apply? Yeah. If it does, determine the, but I'm going to be all like wordy about it because I want to train you to be able to write these as they would need to be written on a free response question if they said justify your answer. So here we go. F of x equals 1 over x is, all right, 3 conditions. Is this positive for all x is greater than or equal to 1? Yes. All right. It's positive. All right, step 1. Is it continuous? Well, not at 0, but that's not an issue, so we're good. Is positive, continuous, and is this consistently decreasing? Yeah, it is. 1 over x is 1 over 1, 1 over 2, 1 over 3, 1 over 4. It's getting closer to 0. And decreasing. Put my Oxford comma in there. I generally don't. For x greater than or equal to 1. So the integral test applies. Okay, fantastic. Let's pause the actual final answer, and the rest of this is going to say, because the integral converges, then the series converges, or because the integral diverges, the series also diverges, because they're going to do the same thing. They either both converge or both diverge. So, switching to the purple pen again, we're going to find the integral from 1 to infinity of 1 over x dx. So let's keep writing. Now, hopefully you noticed already, we can't go to infinity, but we can pretend to with the limit. So the limit as x, not x, let's not do that. X doesn't approach infinity. Oh, whiteout's getting messed up. There we go. B approaches infinity. B, where'd you get B from? Well, because I'm using this integral, and that's usually A, and that's usually B. You can let it be almost anything you want it to be. I wouldn't use N because of this context, and I wouldn't use X because you're going to need X here. But anyway, it's going to start at 1, it's going to go to B, and B approaches infinity, dx. And then we'll just keep integrating. The antiderivative of 1 over x dx is natural log of x. So this is the limit as B approaches infinity of natural log of x from 1 to b. Now, technically, I don't need those parentheses, the absolute value bars on that x because, well, we're dealing with positive values. It goes from 1 and then up from there. But we'll keep going. This is the limit as b approaches infinity of natural log of b minus natural log of 1. Okay. Let's see. Natural log of b, as b approaches infinity, well, that's going to give me, well, infinity, right? And then minus natural log of 1, well, that's 0. So infinity. This integral diverges. Because, about to finish the sentence here, because the integral diverges, the series will also diverge. All right, let's finish the sentence. That seemed anticlimactic, sorry. Oh, and now we write the answer. Because the integral, I'm going back up to here, 1 over x dx diverges. The corresponding series that I'm writing right here, 1 over n, also diverges. Okay, let's do the next one. The next one looks very similar, but it's the sum from 1 to infinity of 1 over n squared. So let's keep going with this, and we're going to start by writing it like a function. You don't have to write the big sentence every single time, but I am for the first two. I'm not going to do it for the other ones. 1 over x squared. I may actually have done it for the other ones. I've actually already filmed the second half of this video without doing the first half, so I forgot if I did or not. Either way, good practice, but I'm not always going to do it. So let's kind of look at this and write a sentence, and y'all know you just wrote pretty much the exact same thing, but the more you write it, the more you'll remember it, and I'm going to go down here to the bottom. So f of x equals 1 over x squared is it positive? Yes, always. It's positive even for negative values of x, but that's not where we're dabbling. Is it continuous? Not at 0, but that's not an issue. And well, and that's not an issue because it starts at 1. So positive, continuous. And is it decreasing? Yeah, 1 over 1, 1 over 4, 1 over 9, 1 over 16. And decreasing for x is greater than or equal to 1. So the integral test applies. All right, let's go ahead and start the next sentence. Because from 1 to infinity of 1 over x squared dx, the next word is either going to be converges or diverges. Then I'm going to say, I'm just getting way ahead of myself here. N equals 1 to infinity, 1 over n squared. Also, also, spelled correctly, does the same thing. I have 2 blanks left to fill in. Let's figure it out. All right, let's do it. The integral from 1 to infinity of 1 over x squared dx. We move on. This is an improper integral, so we're going to go limit as b approaches infinity of 1 to b, 1 over x squared dx. Okay, if you need this next step, do it. If you don't, skip it. Limit as b approaches infinity, 1 to b, of x to the negative 2 dx. Just helps me integrate, and we'll keep going. The limit as b approaches infinity, and we're going to add 1 to that exponent. We couldn't have done that here. We'd end up with x to the 0, and then, yeah, the world falls apart. Natural log, that's the thing to do on that one, but not this one, because the denominator's to the second power, not the first. So we have, let's see, x to the negative 1, 1 divided by negative 1 is going to give me negative 1, and that's going to happen from 1 to b. No need for a c. This is a definite integral, improper though it may be. So limit as b approaches infinity of negative b to the negative 1 minus negative 1 to the negative 1. There's a lot of unnecessariness in there. Let's clean a few things up. The limit as b approaches infinity of, all right, negative b to the negative 1 is negative 1 over b, and then plus, well, just 1. So we are going to have, apparently that's the sound you make when you write an equal, all right, limit as b approaches infinity. Look at this term, negative 1 over huge. Well, that just approaches 0, and the bigger the denominator get, the more this approaches 0. So we're going to have 0 plus 1, which is 1. Okay, that means that this integral, by the way, and this is a fun one, this integral is equal to 1. Who knew? Like, isn't that amazing? I really want to just grab a calculator and show you some really cool stuff right now, but no, that's not the lesson. But this integral is equal to 1, and I find that to be absolutely amazing. So if you were to grab a scrap piece of paper, I'm sorry, I'm getting off topic. Here's the graph of 1 over x squared. It looks like the graph of 1 over x to the untrained eye. This infinite area, and you've seen this before in a previous lesson, this infinite area is equal to 1. I think it's absolutely amazing. But, and this is huge, because this converges to 1, it doesn't mean that the series converges to 1. The area under the curve is a completely different issue than adding an infinite number of terms. In this context, it is a different issue. Now, it can be, they can relate very closely in a lot of ways. But in this context, this area equaling 1 does not mean that this equals 1. This does not equal 1. It equals pi squared over 6. Random thing, don't have to know that, but it's fun to know. But here's the deal. I got 1, I didn't get infinity. Because I got a number, the series converges. Because the integral converges, its corresponding series also converges.